this is the example widget I'm going to demonstrate, right, to show you all the concepts we talked about. Now, unfortunately, I have to preface by saying, unfortunately, I cannot share the code with you, right? But I do believe I've given you all the underlying techniques to create such a widget by yourself or with the help of AI nowadays, right? So what you're seeing is this live eye diagram. So this widget in the background, there's a continuous transient simulation that's being run. The TX goes through a channel, the channel sees a CTLE, right? And then there's a DFE that's possibly we can turn on, okay? And then this knob right here is my sampling phase. I'm acting as the CDR, okay? So as you can see, as I move this cursor on the single bit response over here, the discrete time SBR moves with me. And then on this side, this is showing the frequency response of all the critical blocks, right? The channel itself is the blue curve, right? And then the TX plus the channel is the yellow, and then the TX plus channel plus RX. The RX being mostly just the CTLE is the green, okay? So any sort of equalization that we apply now will change all three pictures right here. It will change the eye diagram, it will change the frequency response, and it will change the single bit response as well. Okay. Okay, so now I actually started with the um, easy channel. It's only a 7 dB loss channel. This is not a lot of loss. So even without equalization, you see that I still have an open eye, right? So let's go through these knobs one by one. So the first thing is your TX swing, right? The TX swing is pretty easy to implement. It's just a simple scaling factor in your code, right? So you can increase it or decrease it. Okay? Now, the first knob for our equalization is TXFIR. So for this particular case, I only have one tap precursor, one tap postcursor. So if I apply precursor, you will see that, let's focus on the SBR over here, right? You will see that the precursor point starts to get dragged down, right? Until I can make it almost zero, right? I can keep increasing the postcursor and drag it down until it's almost zero. And in this particular case, the eye can be made very clean with just TXFIR alone, right? So what you see here in the frequency domain, what's happened is by applying TXFIR, the DC dropped, right? So it was a low pass filter. The TXFIR drops the DC and made it flatter. And when the frequency response is really flat, that's when the eye is equalized, right? That's the whole point of equalization, is to make the frequency domain really flat. That's what we talked about, right? But if I zoom in here, I mean, there's a bunch of residual ISI, right? That's contributing to this little spread, right? And this is where the probability domain discussion we just had came into the picture, right? Like if I look at the sampling point at this point, what this axis is showing is the probability distribution of the noise. And then this is a combination of thermal noise as well as ISI. And then you can actually now know how to calculate all of this with these little sticks right away, right? All right, so let's get rid of my post-cursor equalization on the TX side. Another thing we talked about is the CTLE, right? We said the CTLE could equalize post-cursor as well. So let me turn that on. Okay. So if you turn on that post-cursor equalization, okay. And then I move the sampling point a little bit, right? And then you see that the post-cursor ISI did get cleaned up. Another benefit of CTLE is that it actually increases your signal strength because you can now have gain, which is different from TXFIR, right? TXFIR, I had to drop the DC gain significantly. The CTLE actually did not drop it. It actually just increased the high frequency gain, right? At the cost of noise, of course. So you have the option to now change your zero frequency of the CTLE, right? By moving it down to get to your ISI, cling point, right? So these are the typical knobs that you can have for your CTLE. I can increase my DC gain, decrease my DC gain, etc. Right? So there's this concept of over equalization, right? So what it means is that, let's say if somehow I design my CTLE zero free frequency to be suboptimal, which is something that I'm sure Professor Kim talked about, and that's where you have to design where your zero free frequency is. What will happen is you will get something like this. You will be over peaking your single bit response. You will get an undershoot. And then now, instead of cleaning your ISI, you're introducing ISI in the opposite direction. And that's non-ideal, right? So you gotta be very careful about how to set this, right? Okay. So the last thing we want to talk about is, let me actually now increase the channel loss. So I'm gonna give myself a pretty hard channel. I'm gonna give myself a 20 dB loss channel, okay? So when I say loss scale, all I'm doing is I'm frequency scaling the channel here. So let's turn off the CTLE, let's turn off the TXFI. Okay. So in this particular case, you see that my starting point is pretty bad, right? I don't have an eye opening at all. In the current state, I cannot do any decision and say I can make no mistake, right? As you can see, the PDF is everywhere. It's a bunch of little Gaussians added on top of each other, right? So the SBR also is pretty dirty. It's got big energies at the precursor and postcursor as well, along with a bunch of smaller taps, right? These are the bumpiness in the channel. So let's see what we can do to equalize it, right? So first thing first, I'm gonna add some TX pre-equalization, all right? And then I'm gonna introduce my CTLE, all right? So this setting right now seems to be reasonable. Like I have a little bit of an undershoot here. So maybe I will try to increase it ever so slightly, okay? Just to make sure that I don't over equalize. So right off the bat, you see that I can open the eye roughly already, right? But what's the problem? The problem is, well, let's say I start to add system noise, right? Let's say I start to add system noise. But the eye, you can see that it's effectively closed again because you get these noise that's in the middle. You can make a mistake here, right? You can achieve a similar effect if your TX jitter started to increase, right? So that can be visually seen on the eye diagram. Or you can say my sampling distribution got worse, right? So if you increase that, even though the incoming eye diagram does not change, right? This spread over here is going to change. So I'm going to go back to 0, right? You will see that this spread looks okay. It's slowly going back down, right? There is some sort of an opening here, right? And if you increase that a little bit more, you see that the signal energy starts to come up here, and then you might make a mistake here, right? So basically, all I'm saying is that this is not cleaned up enough, right? We need to clean up this a little bit more. So the only knob that we haven't exercised is the DFE, okay? So there is a technique where we can use our sampling point. So that's where the CDR comes in. Again, we're being the CDR now, but there are things you can do in the CDR to say, hey, instead of keep increasing this on the TXFIR, what I will do is I will move my sampling point forward a little bit. You can see that that effectively canceled this guy, right? And then what's left mainly is just the first postcursor. And then that's what DFE is very good at in terms of canceling it. So we will just keep increasing the DFE. Voila. Now the eye is more wide open, right? And then the reason why we want to do DFE is because it's more immune to noise in the system, right? So these are the equalization knobs we talked about. Now, I obviously can go crazy with a lot of DFE taps. I'm going to set it to 16, and instead of manually finding all the coefficients, there are algorithms to make them auto-adapt, right? So when you adapt them all together, they can cancel each one correctly, and then you can get a super clean eye. Now, this is more of a system decision now, right? Given a channel, how many taps do I really need to meet my SNR spec, right? Or to meet my BR spec, right? And then these are the sort of the games that we play once the numerical model is available. Now, of course, like this is a widget that shows a live demo in a production simulation. We don't really do this by hand, right? A lot of these are scriptified, and we run long simulations in parallel and trying to figure out all those design space. But this gives you a pretty cool visual idea of what's happening, right? And last but not least, what I want to showcase is, this is not what we deal with today. What we deal with today is PAM4, right? In a PAM4 space, we do have another equalizer available, which is FFE. I do not have the widget here, but in the future, I might want to add it. But the idea is the same, right? Now you basically just send 4 levels. But as you can see, when I don't do PAM4, NRZ alone gives me enough margin to not make a bit error. As soon as I go to PAM4, the eye effectively is closed again because I have to squeeze 3 eyes within the same voltage level. So I need to clean up more ISI just to get myself more margin. So PAM4 is definitely more difficult. That's why we have more sophisticated equalizer to handle them. All right. So this is the demo that I wanted to show you guys, and then hopefully this kind of closes the loop, right, for everything we kind of talked about today.